we are going to look at the last three sections altogether, understanding that the position of an electron in an atom is not known with certainty. Only the probability of the electron being at a given point of space can be calculated. This is a consequence of the Heisenberg uncertainty principle. And we're going to understand the modern view of atoms describing electrons as waves and identifying orbitals as allowed quantized energies, describing the allowed energy states of orbitals in an atom using 4 quantum numbers, and describing the shape of orbitals. Erwin Schrödinger's model of the atom improves upon the Bohr model in a few distinct ways. His model replaces the one-dimensional circular orbits with 3-dimensional orbitals, providing a probability of finding an electron. The Schrödinger model assumes that the electron is a wave and tries to describe the regions in space or orbitals where electrons are most likely to be found. The 3 coordinates that come from Schrödinger's wave equations are the principal, N, the angular, L, and the magnetic, M, quantum numbers. These quantum numbers describe the size, that's our N, the shape, our L, and the orientation in space, which is our ML, of the orbitals on an atom. So there's one more important concept to touch on as we try to understand the modern quantum mechanical model. In Bohr's model of the atom, both the energy and location of the orbit for the electron and the hydrogen atom can be described accurately. However, Heisenberg postulated that for a tiny object such as an electron in an atom, it is impossible to determine accurately both its position and its energy. So any attempt to determine accurately either the location or the energy will leave the other uncertain. This is now known as the Heisenberg uncertainty principle. If we choose to know the energy of an electron in an atom with only a small uncertainty, then we must accept a corresponding large uncertainty in its position. Let's look at this. This video from YouTube shows the Heisenberg uncertainty principle that's explained intuitively.
Say there's this little old lady, Mildred. Now you've been watching her for a week and you notice that on Sunday she goes to the market. Now, can you conclude that every Sunday she goes to the market? Well, not really. You've only seen her do it once. Now, you watch her for another week and lo and behold, on Sunday she goes to the market. So it's tempting to say that she goes to the market with frequency once per week. But it's still not enough. You need more time to draw an accurate conclusion. After a year of careful surveillance, you're pretty sure that she goes to the market with frequency once per week. But what if the next week she goes to bingo instead? Or what if she needs more cat food and goes twice? Really, you need an infinitely long time to be 100% sure that Mildred frequencies the market once per week. Obviously, you don't have an infinite amount of time. So the frequency of Mildred's market trips can never be known to 100% accuracy. There's this trade-off between knowing the frequency and spending time. This is a version of the uncertainty principle, and variables that have this trade-off relationship are called conjugate variables. Another more well-known pair of conjugate variables are position and momentum. This is one version of the Heisenberg uncertainty principle, and it states that the uncertainty in position and the uncertainty in momentum are always greater than or equal to this constant here. Basically, we can never measure both the position and momentum of an object to 100% accuracy. We'll come back to the equation in a bit, but first, let's talk about the intuition. The way my quantum physics professor introduced the uncertainty principle was, imagine you're trying to find the location of a basketball, but the only way you can do that is by throwing tennis balls at it and measuring where they bounce back. If you manage to hit the basketball, sure, you know where it was, but now it's moved. Keep the imagery in mind for this next bit. Heisenberg was a German physicist who loved classical music and was a pretty accomplished piano player. Oh yeah, and he won the Nobel Prize for the creation of quantum physics. One day he was performing a thought experiment. He wanted to see if he could measure both the position and velocity of an electron. To measure the velocity of something, you just need to measure its position twice and divide by the time it took between each measurement. So it seems silly that you could measure something once, but not twice, right? But the most direct way of measuring where something is to shine light on it, and from the reflected light, calculate its position. We do this every day when we look at things. Photons hit the object and reflect them back into our eyes. Then our brain figures out where it is from the image produced on the retina. So Heisenberg imagined looking at an electron under a microscope, firing a photon at it and figuring out the position of the electron. But in order not to move the electron, he would need to hit it with a photon of really low energy. Now, quantum particles have a property called wave-particle duality, where they behave as both particles and as waves. So while they can be thought of as particles, they also have a wavelength and frequency. Radio waves have the longest wavelength, 30 centimeters or more, and they're great for capturing images of stars and planets. But they'd be hopeless at producing a good image of, say, your face. You would just get a blur. See, you can't get better focusing power than the wavelengths that are forming on the image. The 30 centimeter radio waves can only make images of details at least 30 centimeters big. If you made the wavelength smaller, to about a millimeter, then you'd get a much better image. So if Heisenberg wanted to get a clear image of an electron, say to within a micron, he'd need to decrease the wavelength of the photon to within 1,000th of a millimeter. But the energy of a photon is given by this equation, where E is the energy and lambda is the wavelength. So you can see that as the wavelength gets smaller, the energy gets bigger. If we decrease the wavelength, allowing us to get an accurate description of its position, the photon has to be of such high energy that it hits the electron too hard and moves it. If we hit the electron with a photon of low energy and then hit it again, we can get an idea of the velocity, but the images will be too fuzzy to measure its position with decent accuracy. This is a conundrum. Position and momentum are conjugate variables. You can't gain information about one without losing information about the other. As we saw from Heisenberg's experiment, this had nothing to do with the equipment he was using. Unless we find a way to make wavelengths shorter without increasing energy, we're screwed. Now, for those of you who need a mathematical description to go with the intuition, don't worry, it's coming. When Einstein concluded that light behaved as particles, this French guy named de Broglie made this outrageous, totally not founded on anything claim that all particles must behave like waves too. And he was right! The wavelength of an electron is just Planck's constant divided by its momentum. Therefore, the momentum of a wave can be represented by a wavelength.
We're moving on to introduce quantum numbers. I want you to think about a coffee mug and 4 different ways to think about how a coffee mug is oriented. Think about first your favorite coffee mug, and we want to think about what size it is on a scale of 1 to 6. 1 being very small and 6 being very large. In this case, the number that I'm thinking of, I'm going to give it a value of 2. It's not the smallest you could think of, like thimble size. We're going to call it a 2 out of 6. Second thing I want you to think of about that coffee mug, what shape is that coffee mug? Is it a traditional shape? Is it cylindrical, so like tall and shaped like a cylinder? Is it like a bowl shaped, or is it kind of a funky shaped? I'm going to go with a traditional shape, which is a value of 0. So this is my L, and it's actually a little cursive L. How is your coffee mug oriented? Is it upright on the counter? Is it upright in your pantry? Is it upright in the dishwasher? Is it on its side? Is it upside down? Give it a value of -1, a 0, or positive 1. For me, I'm going to give mine a value of -1 because it is upright sitting on my counter. And then lastly, is the handle to the left or to the right? If it's to the right, we're going to give it a value of +1/2. If it's to the left, -1/2. Mine, I'm giving a value of -1/2. The handle is on the left. So I could give you 4 numbers here, an N, an L, an ML, and an MS. And this can tell you a lot of information about how my coffee mug is oriented and what it looks like and where everything is. For example, I can say that it's a 2, so it's pretty on the small side. It is a traditional shaped, it is upright, and the handle is on the left. This is going to allow us a way to describe where electrons are found in an atom. First thing you need to know is some information about orbitals, where electrons are found. S orbitals have one s orbital within that orbital. S orbitals are spherically shaped. This is an example of what a 1s would look like. It's small, and as I get bigger, this would be 2s and 3s. you can see that as I get further from the nucleus, as my N value gets larger. These are my p orbitals. There are 3 p orbitals. These are my d orbitals. There's 1, 2, 3, 4, 5 d orbitals. And these are my f orbitals. 1, 2, 3, 4, 5, 6, 7. There are 7 f orbitals. Now if you look at your periodic table, the elements found in my s orbital are these guys. And I told you that there is 1 s orbital. 1 orbital can hold 2 electrons. So let's go back to our periodic table. In my first S, I can hold hydrogen and helium. Helium goes over here, fits in right there. In 2s, I can hold 1, 2. In 3s, I can hold 1, 2. In 4s, I can hold 1, 2. And again, both of these in 1s fit in 1 orbital. 2s, those 2 fit in 1 orbital. 3s, those 2 fit in 1 orbital. 4s, those fit in 1 orbital. 5s, those 2 fit in 1 orbital. 6s, those 2. 7s, those 2. So these first 2 columns are my s block electrons. We said there are 3 p orbitals. Let's look at the periodic table. Again, each orbital holds 2 electrons. So if there's 3, that means that 1, 2, 3 orbitals can hold 6 electrons. 1, 2, 3, 4, 5, 6. So there are no p orbitals in energy level 1, but there are in energy level 2, 3, this is 4, 5, 6, and 7. These are all p orbitals. This is 3p, there's 3 orbitals, 4p, 5p, 6p, and 7p. There are 5 d orbitals. This is my d section. 5 d orbitals times 2 electrons per orbital is 10 total electrons. 1, 2, 3, 4, 5 orbitals times 2 is 10. Now, yes, this first d row is in energy level 1, 2, 3. You would think it would be in 4 because these are my 4s electrons. But when we get to this row, this is actually 3d. And down here, starting with number 39, is 4d. 57 is 5d, and this is 6d. Again, 2, 4, 6, 8, 10, and there are 5d orbitals. Moving down to the f orbitals, there are 7 orbitals. I'm going to start from the right here. 2, 4, 6, 8, 10, 12, 14. This number 57 and 89 go up here into 5d and 6d. So there's 1, 2, 3, 4, 5, 6, 7 orbitals in the f orbitals that hold 14 electrons. And in the f, yes, it is in row 6, but similar to the d electrons, how this 3d is in row 4, so these d electrons are 1 less than the energy level that they're in. The f's are 2 less than the energy level they're in. So this is actually 4f, and this is 5f. Quantum numbers are terms that arise from the mathematics of Schrodinger's equation. They describe the location of an electron in a particular orbital, much like an address. Let's think about how an address works. I'm going to start with the last part of an address, how there is a zip code. And a zip code shows us a wide area within a state. And then we can be even more specific, and within that zip code, we can specify a city. And within the city, we can be more specific and look at what road a person lives on. And then the most specific part of an address is the house number. There are a lot of people that live in a state, fewer people that live in a zip code, fewer people that live in the city, even fewer people that we can narrow down that live on that road, but there is only one person that has that specific house number on an address. We can relate quantum numbers to this. It's telling us the location of an electron, and we get more and more specific as we look at each quantum number. There are 4 quantum numbers. We're going to start with the very broad principal quantum number, which is which energy level is it? Are we energy level 1, 2, 3, 4, 5, 6, or 7? To tell that, we can look back to our periodic table. If we are in row 1, that is energy level 1. Row 2, row 3, row 4, 5, 6, and 7. That is our principal quantum number. It tells me my shell. Then we have our L, our subshell. And that tells me, are we in the S orbit, the P, D, or F? We give that a number value of 0, 1, 2, or 3. I'll show you more in just a minute. Then we have our individual orbitals within that subshell, and we'll get to the last one in a minute. Let's look at those 3 a little bit deeper. If I said n equals 1, that means period 1. N equals 2 is period 2. N equals 3, it does get a little bit trickier here because n equals 3, it's not just row 3. I'm going to go back to our periodic table here. This is 1, this is 2, this is 3. We have 3, we have these guys, so we have 3s, we have 3p, and these first row of my transition elements, they are found in 3D. So yes, it is in row 4, but these guys are 3D. That's where that comes from. So period 3 and the elements that are transition elements, 21 to 30. Now let's look at row 4. This is row 4. So I have 4s, I have 4p, these guys, and then just like this is 3D, this next row down of transition elements, that goes with 4. That's D. And right here in row 6, but way down here, these lanthanide and actinide series, not 57, but 58 through 71. This is my 4F. So those are that's the transition metals, and that's the 4Fs down at the very bottom. We look at row 5, so that's period 5, and we've got my transition metals and my bottom ones. So this is my 5S, my 5P, 5D, 5F. We'll stop there. How do we label those S, P's, D's, and F's? So we have our N, which is telling me is it row 1, 2, 3, 4, 5, 6, or 7. Then we show our L's. If it's in the S, we give it a value of 0. P is 1, D is 2, F is 3. So our L values are either 0, 1, 2, or 3 for S, P, D, and F. Now within S, P, D, and F, we have those orbitals within the orbital. We said S has 1 orbital because only 2 electrons can fit. We give that 1 orbital a value of 0. So 2 electrons can fit in that 1 orbital. Its ML value is always 0 for S. We said that there was 3 orbitals in a P subshell. We give it a value of 0, +1, and -1. And it would look like this. I'm going to draw the 3 orbitals within that P orbital, and we give the middle one a 0 value. To the right, we give a positive one, to the left, a negative one. That's our 1, 2, 3 options. For D, there were 5 orbitals, which can hold 10 electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We give the middle one a 0, +1, +2, -1, -2. And for F, can hold 14 electrons, so 7 orbitals. 1, 2, 3, 4, 5, 6, 7. It would look like this. 1, 2, 3, 4, 5, 6, 7. The middle one is 0, +1, +2, +3. And to the left is -1, -2, -3. Like I said, each orbital can accommodate no more than 2 electrons. Since each electron is unique, we need a way to distinguish the individual electrons in an orbital. This is done with a 4th quantum number, which we say is ms. That tells me the spin of an electron. One electron has a spin going up, and the other is spinning going down. So we say that ms is either plus 1/2 or minus 1/2. Plus 1/2 as it's spinning up, minus 1/2 as it's spinning down. If we have paired electrons, we say that it is diamagnetic. And diamagnetic substances are not attracted to a magnetic field. If there's unpaired electrons, we say that it's paramagnetic. And paramagnetic substances are attracted to a magnetic field. So a quantum number summary here: no two electrons in an atom can have the same set of 4 quantum numbers. Just like two people cannot have the same address. You can have the same zip code, you can have the same city, you can have the same street, but you can't have the same number on your house. No two electrons can have the same 4 quantum numbers. They could have 3 out of the 4, but the 4th one is always going to be different. Which of the following is not a valid set of quantum numbers? Can I have in my 4th energy level, can there be a p and an orbital of a -1? Sure, that would be 4p, and there would be 1, 2, 3, 0, -1, and a +1. Yes. In energy level 6, can there be a p with a 0? Sure. 6p, and there's 1, 2, 3. The 0 is the middle one. 6. 1, 2, 3, 4, 5, 6. That would be 6, and I have 6 different p's. So yeah, that would be an option. What about in energy level 2? An L of 2 would mean that there would be a d electrons. Does row 2 have d electrons? No, that is not possible. Row 2 can only have s and p, so a 0 or a 1 for L. Let's just make sure that this doesn't work. Row 3, can I have d? Yes, it can. For a certain orbital, 3p -1, what type of orbital is this? Oh, it's a 3p. If an electron has 7 orbitals, what is the L value? Or 7 orbitals, that means that it's got to be an F, right? And so 0, 1, 2, 3, the 0 is S, P, D, F. It's got to have an L value of 3. That wraps up Chapter 6. And while you are probably left with a lot of questions, Chapter 7 is going to go a lot more in depth of drawing electrons and figuring out how to specifically write the quantum numbers for different elements in particular.